So in this video, we will be talking about kinetic energy. So anything that moves has kinetic energy, like my ass cheeks that jiggle like crazy. And bro, why did I say that? Oh my god, bro. Okay, I'll just show you the formula. Kinetic energy is just 1/2 mass times velocity squared is equal to kinetic energy. Keep in mind, kinetic energy, since you square the velocity, you're just squaring the speed, basically. So kinetic energy will always be positive. Since mass is positive, 1/2 is positive. You square anything, it becomes positive. All these terms are positive, positive, positive. So kinetic energy must be positive. Now, one key thing to point out is as the velocity increases, your kinetic energy exponentially increases. Hence the squared value here. And likely your mass will not change. So that's just an important relationship to bring light to, or at least point out. But let's move on. Let's move on to some problems. So my first problem: 8-gram bullet, speed of 800 meters per second. What is its kinetic energy? So just use the kinetic energy formula here: 1/2 mass velocity squared. And okay, mass of the bullet. Mass of the bullet is, well, this is 8 grams, so we need to change this to kilos. So we have 0.008 grams, kilograms. Oops. Okay, now that we have the mass, multiply the mass by my 1/2, and your velocity is 8 meters per second, or speed, squared. Put this into a calculator. You get 0.008 times 800. You get a kinetic energy of 2,560 joules. Okay, part A, done. Part A, done. That was easy. It's just one step. Okay, what is the kinetic energy if the speed is halved? So if the speed became 400 meters per second, since that is 1/2 of 800. Let's just calculate that. Mass stays the same. Still 8 grams, or 0.008 kilos. Let's calculate your mass. Let's calculate with half the velocity, not calculate the mass. So what happens is your kinetic energy exponentially goes down. So even though your velocity was simply halved, so 1/2, V's 1/2, your kinetic energy, your KE, is 1/4 due to the squared property of the velocity. So that's important to know. It's a good relationship to be aware of. Compare the kinetic energy of a 20-kilo truck moving at 110 kilometers per hour with that of a 80-kilo astronaut orbiting at 27,500 kilometers per hour. Okay, we need to do some unit conversions. So let's do that. So km per hour. Let's convert kilometers first. So we have 1 km down here, and then 1,000 meters up here. The unit for kilometers cancels. And we also have the 1 hour, so we put the hour at the top, and we have 3,600 seconds. The unit for hours cancels, and we get meters and seconds here. So all we need to do is multiply 110 by 1,000 and then divide it by 3,600. Sorry. So you get a speed of 30.56 meters per second for the truck. Okay, let's find the speed of the astronaut. So the speed of the astronaut is, again, using some unit conversion. Same unit conversion multiplied by 1,000 divided by 3,600. Then you will get, okay, I need to type this on my calculator, give me a sec. You will get a speed of 7,638.89 meters per second. So we just need to calculate our kinetic energies for both of these. So this is the kinetic energy formula of your truck, and the kinetic energy of the truck is 9.34 megajoules. So megajoules just stands for 1 million joules. So if you were to round this up, you would get a kinetic energy of 9,340,000 joules. So the formula for your astronaut is this right here, and your kinetic energy is 2.34 gigajoules. Now, good relationship to know is, of course, velocity or speed matters the most, matters way more when it comes to kinetic energy. So the kinetic energy for this astronaut is more than, or close to, actually it's not more than, it's like 30, no, it's like 300 times, close to 300 times greater than the truck. Even though the truck weighs, who knows, like 2,000 times more? No, 200 times more than the person. Since this astronaut is orbiting faster, it has a higher kinetic energy. But crazy thing is, it would be more devastating for this astronaut to hit something. So if the astronaut hit something, it would be way more devastating than if the truck were to hit something, due to the sheer amount of kinetic energy this is. This is 2.34 billion joules, by the way, if you didn't know what giga meant. But let's move on to the next problem. In this problem, you have a elephant and a sprinter. So you just wanted to compare how fast must a 3,000 kilo elephant, so the mass of 3,000 kilos, be in order to have the same kinetic energy as a sprinter with 65 kilos. This guy's pretty damn light. At a speed of 10 meters per second. So we want to set the equations equal to each other. So you have 1/2 of 3,000, this is the elephant side, times some unknown velocity. So the velocity of the elephant, VE of E, is equal to 1/2 of the kinetic energy. This is the kinetic energy formula for the person. 10 squared. So all we can actually just cancel out the 1/2, and when we isolate V of E, doing some little bit of algebra, we get that the elephant just has to move 1.47 meters per second. So this elephant significantly needs less speed in order to have the same kinetic energy as the sprinter. So this is part, where did I write part A? Part A, right here. Okay, let's solve for part B. So part B. Part B is discuss how the larger energies needed for the movement of large animals would relate to metabolic rates. Well, in order for an animal to move, okay, this is just a more conceptual problem, so I'll just explain this to you. I don't even need to write down the part, actually. In order for an elephant to move at 1.47 meters per second, it needs the same amount of energy as a sprinter running at 10 meters per second, which is very, very fast. I'm pretty sure that would qualify you for at least a Texas high school like track states. But 10 meters per second, 100-meter dash is 10 seconds, which is pretty close to Olympic times. If you could run a sub 10, I'm pretty sure you made it to the Olympics, actually, for track and field. But elephant needs significantly more energy to move at some very, very much lower speed compared to a human sprinting. So I guess that would be an explanation how part B works. So as always, I have to mention OpenStax. So OpenStax, free online textbook, I get their problems from there. I'll have a link in the description. But an important note is that I'm going to have a video. So when I post that video, I'm going to connect work and kinetic energy. And I'm going to connect them by stating that work is equal to the change in kinetic energy. And this is called the work energy theorem. So learning about work and learning about kinetic energy, both of these are important, but in order to connect them together is even more important. So I'll have a link in the description for this when I post it. But as always, if you have any questions, put it down in the comment section. I hope this video helped.